This is YR, Women in AI Research. In this EACL 2026 series, I'm speaking with authors of accepted papers to break down their work and the ideas behind it. Let's dive in. Hi, could you please introduce yourself?
Yeah, hi. My name is Iwona Christop, and I am a PhD student at Adam Mickiewicz University in Poznań, in Poland. And I'm working mainly on audio processing.
Amazing. And I see you have this work on audio reasoning tasks that was accepted to the EACL main conference track this year. So could you please walk me through this work?
Yeah, sure. Actually, it's a paper, a benchmark for audio reasoning capabilities of multimodal LLMs. And it's a work that we've done in a cooperation between Adam Mickiewicz University and Samsung R&D Institute in Poland. So I have 6 co-authors. And the main idea, the main motivation behind it was that there are some benchmarks for evaluating the audio skills of LLMs, but they test the skills in isolation. So, for example, we have automatic speech recognition, which is a transcription, or we have audio classification or something like that. But these benchmarks don't evaluate the reasoning that we know from, for example, ChatGPT or other LLMs. Yeah. Also, all of these benchmarks, sorry.
No worries.
Many of these benchmarks, they rely on text prompts, which means that the question that is asked in a text prompt, and then we have a sound the question is about. Also, they tend to use the LLM as a judge, where the LLM decides if the answer is correct or not. And sometimes they even use the same LLM as a judge as the one that they are evaluating. So it introduces some kind of bias. And also, the third main thing is that some of these benchmarks, they require expert knowledge. Because, for example, we have questions about chords, about tones. We don't all have expert musical knowledge, you know? So we can't really know if the LLM is right.
Mhm.
And that's why we decided to create the audio reasoning tasks, which is ART for short. And we decided on a few key rules that we wanted to employ. Okay, so we wanted to focus on the reasoning, and we decided that the problem shouldn't be solvable by just analyzing an output from a single module. It means that if we take one of our questions, one of our tasks, and we do a transcription of it, the LLM still shouldn't be able to solve it because it would be too simple. The second thing is that we didn't want to include any musical or engineering knowledge in this tasks because we wanted them to be solvable by everyone, so that everyone can actually verify if the answer is right. Also, we decided that the questions also should be spoken, not written, because as I mentioned, benchmarks rely on text prompts. So, for example, we have does the dog bark an even number of times? And then we have the barks. And the last thing is that we decided that each question should have an yes or no answer. Because this way we don't need an LLM to serve as a judge. It's just binary, you know. Okay, so this way we actually created 9 tasks, which equal to 9,000 samples. and that equals to over 30 hours of audio recordings. And we decided on these 9 tasks because we assembled a team at first, and everyone gave some ideas of what the tasks could be, and then we eliminated a lot of them so that they could just first not be solvable from a single module, don't require an expert knowledge, and also we decided to not include any tasks that could be subjective, like emotions and things like that. Okay, so we have 9 tasks. We have audio arithmetics. That's the one that I've already gave example, where we ask a question that requires performing some simple calculation about the sounds. So here we have, for example, are there as many bell rings as there are cat meows? So the question is being asked, and then we have, for example, 3 bell rings and 2 cat meows, and the model can respond with yes or no. Then we have the audio transformation detection, where we have 2 recordings, and one they can be the same recording, and one of them is, for example, sped up or louder, or they can be 2 completely different recordings, and yeah, it still comes to a yes or no. Then we have cross-recording language identification, where we have utterances in a few different languages. So, for example, the question is Budapest the capital of the country the speaker comes from? And then we have an utterance in, for example, Polish language. Then we have the cross-recording speaker identification, where we just ask if the same speaker is heard on both recordings. Then we have selective text inference. This is a really interesting one, because, for example, we have 2 questions. One asked by a man, second asked by a woman, and the main question is green the answer to the question asked by a man? So the model has to recognize the gender of the speaker and then analyze if this is the correct answer to this question. Then we have the sound reasoning, where we have 2 sounds and we need to compare them. For example, is the animal that makes the following sound bigger than a horse? And then we have, for example, a dog. Then we have the speech features comparison, where we can have 2 utterances which have the same text, but one of them is, for example, with a British accent, and the second one is being said with a Scottish accent. Then we have text and sound reasoning, where we ask, for example, is the person talking about the following sound? Then the person can say the airplane soars high above the clouds, and then we have a sound of an airplane. And the last one is temporal localization reasoning, where the model has to not only understand what the speaker is saying, but also their background. So, for example, the model has to say if the speaker is at a concert, and the speaker can say something that could actually suggest that he is at a concert, but the background suggests that he is, for example, on a football game. We decided to prepare templates that would allow us to easily generate more and more samples. So all the questions are actually generated using text-to-speech model. Then from a database of utterances and a database of sounds, we can just randomly draw the recordings, and the yes or no answer comes out just by comparing the names of the audio recordings, because we have an utterance which can be named airplane wave, and then we have doorbell wave, so we naturally know the right answer. And this, as I said, this allowed us to generate more and more samples. And also it's important because we are aware that when these samples are public, can be used, they shouldn't be, but they can be used to train models. So with the templates, we can still generate new ones that wouldn't be in any train set of any model. And also, it's important that this data set is fully balanced. So in this 9,000 samples, we have 1,000 samples for each task. And in this 1,000 samples, we have 500 yes and 500 no answers. And the results are actually really interesting because we did a human evaluation and we achieved an average of 93%. So it suggests that these tasks are actually easy and everyone can solve them. But the models fail. They really fail. We evaluated actually a lot of models, but on the poster we can see just 2 examples. Here we have Whisper Large and Quen, where we just did a transcription with Whisper and gave this transcription to text-only Quen. And this model achieved 56% of accuracy, so it's close to random. And we have Audio Flamingo 3, which is an end-to-end audio model. And it also achieved a really close accuracy to Whisper plus Quen, which is 55%. Yeah. And why these models fail? First of all, a lot of models actually provided transcription of the audio recording instead of actually answering the question. We actually gave them in a text prompt just a short instruction, answer the question from the audio, so they know what to do. But they still provided transcription instead of actual reasoning. They also tended to describe the speaker instead of answering the question. So, for example, they answered, "Oh, the speaker is a woman." For a question, is the animal that makes the following sound bigger than a horse? So it doesn't make sense. Yeah. They also missed that that any sound or utterance other than the actual question are present. They hallucinated from the real world knowledge. So, for example, we also evaluated Ultravox, and it tended to do it a lot, especially in this audio arithmetic task, where, for example, does the dog bark an even number of times? The Ultravox answered based on how many dogs are there on Earth and how often they bark, and could it be an even number of times?
I wonder, do you have the results per task? Is there, based on your experiments, is there a specific task that is the most difficult, or it's like all the tasks are difficult for?
Yeah, they are all difficult, but the easiest, as we can say, was the selective text inference.
Mhm.
But to say that it was the easiest is, yeah, the average accuracy on this task didn't exceed the 50% across all models. So yeah.
I see. With human baseline, you have
Mhm.
93%.
Yeah.
Where do those 7% of error?
Yeah, they actually come from the speech features comparison task.
Uh-huh.
Because we found out that the group of people that we've assembled, they weren't so good in distinguishing Scottish, British, and other accents. So yeah, that was
No
the issue.
surprises here. That's a very interesting work. And um, one last question. What is your intuition? You have compared those two situations, first where you use speech to text, and then the text only model to produce the answer, and the model like Audio Flamingo that is just like based on audio. Um, do you see any differences here between those two model types? And also, do you see whether like the source of errors comes from the transcription more, or from the actual textual reasoning more?
Well, I think the biggest issue here is that these models they either understand speech or they
Mhm.
understand sounds. It's like they can't just combine these things. You know, they focus either on the question or either on a sound that they hear.
I
But
see.
yeah, and I think that's why the results are so similar, because you know when we have the Whisper plus Quen system, there were no sounds. The Quen didn't get any sounds. It always got only the transcription.
Mhm.
So when we had the audio arithmetic tasks, there was just the question, no bell ring, no cat meow, anything. So I think that the audio models should perform better, but it's hard to say anything because you know these are really random answers. We also did uh, a second version of the experiment where we where we allowed the models to give us a descriptive response. They didn't have to answer only yes or no. They could answer with a full sentence. And here we used two LLMs as judges, Llama and Quen, and the results weren't better. You know, they were also really random, uh, and also we saw that Llama tended to mark the answer as correct for the models that were built upon Llama, and Quen
Mhm.
actually gave more correct answers to the Quen models. So
Right. Well,
it's
that's
really
a known
hard to,
issue that they have that
yeah,
bias, but yeah.
yeah, it's hard to say why exactly these models fail, because they just can't reason on audio.
Links are in the description, both the paper and the author. Like this video and subscribe to the channel to follow this series. See you next time.